All right, good morning, guys. Today is Wednesday, April 1st. We're going to be looking at section 3.2, day 2, essentially. And I want to just kind of take stock of where we're at right now before we get into what we're going to look at today, because today should actually probably be relatively simple. Obviously, there'll be some harder problems depending on the types of derivatives we're having to find and stuff like that. But here's basically what we've been looking at so far. When we're given a function f of x and we turn it into its derivative, okay, when we turn f of x into the derivative of f of x, what that allows us to do is it allows us to set it equal to 0, or if it's a fraction, figure out when its denominator equals 0 in order to find any critical numbers. Okay, so the whole concept is we've been looking for these critical numbers, and if we say that we had, say for instance, a function has two of them, the critical numbers are -2 and +2. What that tells us is this: at -2 and at +2, we're basically looking for, and we've done, it's actually, I think, essentially day 3 of this section. The first part we were looking at is just what's happening on the sides of those critical numbers. So like at -2, we're plugging in -3 into the derivative to see if it's a positive or negative, because that'll tell us if it's a positive or negative slope. So let's say to the left of -2 you get a positive slope. That means that your graph is going up, and it's going up consistently until you hit -2. And then maybe in the intermediate here, in between -2 and +2, you get negative numbers for your derivative when you plug them in. So when you plug in 0, you get a negative number. That means between -2 and +2, your graph is going down, because that's obviously what it means to have a negative slope, is it's a graph that's going down from left to right. And then at +2, let's just say that it switches gears again. You plug in +3 to your derivative, because that would be a number bigger than our critical number, and here's what we get. We get a graph that's going up. So to kind of go through the sequence of days, the first day that we looked at this, so yeah, I should definitely change this to day 3. The first day we looked at this was we were just looking at what's happening in these intervals. Is our graph going up or is it going down? Monday, what we looked at is what do those intervals tell us about our critical numbers? So what we would have said yesterday, or excuse me, on Monday and into Tuesday, was at those 2 points, what are they? Are they relative maximums, or are they relative minimums? Okay? And obviously what we did, or what I had you guys doing, was I didn't just have you writing relative max at -2, relative min at +2. I had you actually plugging those back into the original function, plug them back into f of x to figure out what they are. So maybe it's -2, 3, and +2, -2, whatever the case may be. That's kind of where we left off, right? Now, what I want to talk about just real quickly before I show you what we're going to do today is this. I want to explain, because I know you guys have seen this before, I just don't remember if we've specifically talked about it in the last couple weeks. The word relative, okay? Relative is considered a local extreme. What that means is this: -2 at -2, 3, that is a relative max, and what that relative means is it's bigger, or it's above, points to the immediate left and right of it. But it's not called what we call an absolute max, because it's not the collective highest point in the graph, which we can see. This arrow over here indicates that this graph continues to go up forever. So points over here, when you get up high enough, they are higher than this max over here. That's what makes this a relative max instead of an absolute max. Okay? So when it comes to these extremes, these maximums and minimums, we have what are considered relative maximums and absolute maximums. We have relative minimums and absolute minimums. This is considered a relative minimum for the same reason. This arrow over here on the graph indicates that the graph doesn't stop there, it keeps going. Well, any one of these points over here are going to be lower than this minimum, okay? So it's a pretty simple concept, the difference between relative and absolute extrema. And I know you guys probably don't struggle terribly with that, okay? Now here's the other part. When we enclose an interval, Okay, when we do something like this, if I tell you I want you to interpret this graph, but I only want you to interpret it on the interval from +2 to +6. What that basically does is it takes +2 in my domain, 3, 4, 5, 6, and what it does is it essentially closes off that portion of the graph. Okay? So this is going to be one kind of interesting part about today, is you're going to have set parameters or set interval restrictions. You're going to be looking at a function today. You're going to be finding its derivative. You're going to be determining if there are if there are maximums or minimums. But here's the weird part. It's not maximums and minimums for the whole graph. It's just for the portion of the graph that's in that little bubble, that little interval. Okay? So with that kind of in mind, I want to show you an example of what we're doing today, but I wanted to have kind of a picture to refer back to so that you didn't have to kind of get a mental picture of what exactly is going on, okay? So let me give you a real simple example to start with here, okay? Here's a quadratic function. F of x equals x squared minus 6x plus 2. And the interval that they're going to ask us to explore is the interval from 0 to 5, including 0 and 5. That's what the brackets here indicate. But here's what it's going to ask you to do. It's going to ask you to find the maximum and minimum values of this function in this interval as far as its graph goes. So we're going to find, if we want to think about it, like an absolute max and an absolute min, but not for the whole function, just for the portion of the function in this window. So I might even give you a picture to go off of that one in just a second here, okay? But here's how we do it. We have to do basically the same thing that we've been doing. We have to figure out if in this range here from 0 to 5, we have to figure out if there's any critical numbers in there. So the first thing we do is the same thing we've been doing. We find the derivative of our function so we can analyze where the critical numbers are. So the derivative is 2x minus 6. And like we said up here, to find our critical numbers, we set it equal to 0, and then we solve for x. So if you set that equal to 0, add 6, divide by 2, you get x equals 3. So here's what this tells us. In this interval from 0 to 5, there is a critical number at 3. Okay? We don't even necessarily need to do a lot of the extra work that we talked about up here. We don't even really have to worry about, because here's the thing: we're not trying to figure out where the intervals are increasing or decreasing. All we're really looking at right now are these points: the endpoint 0, the endpoint 5, and the critical number 3. Just bear with me and let me show you the work that you're going to do today. Then we'll talk about what's like kind of the analogous case of what's actually going on here, okay? So all we do today is this. We take our endpoints, 0 and 5, and then if a critical number emerges in that domain, we plug that in as well. And all we have to do is plug those numbers back into our original function to figure out which one of them is the highest point and the lowest point. Again, the directions say find the maximum and minimum values. Okay? So here it is. When you plug in 0 back to your function, it's 0 minus 0 plus 2, so you get the point 0, 2. Okay? When you plug in 3, 3 squared is 9. 6 times 3 is 18. 9 minus 18 is negative 9, plus 2 is negative 7. So we have the point 3, negative 7. And then 5. 5 squared is 25. 5 times 6 is 30. 25 minus 30 is negative 5. Plus 2 is negative 3. So here's our points: 0, 2, 3, negative 7, 5, negative 3. All we're looking for is which one of those is the max value and which one is the min value, meaning which one's the highest y-coordinate and which one is the lowest y-coordinate. Well, obviously of these three y-coordinates, the lowest one, we can say our min is negative 7. And of negative 3 and 2, 2 is the highest positive point. So there is a max value. The max is positive 2. Let me show you, because this is a super simple one. We go into this knowing that a quadratic equation is a parabola. Okay, so this is a parabola that has only one extreme. It's a parabola that opens upward, so that extreme is a minimum. Okay, the minimum, when we determine that based on its derivative that there's a critical value at 3, that means that the parabola's vertex is at 3. So this is the point over 3 down 7. That's the actual vertex of this parabola. Okay, the two endpoints kind of give us an unequal mirror image of the parts of the parabola that we're looking at. 0, 2 is way up here, and then 5, negative 3 is somewhere like this. So basically here's what we have. We have this part of the parabola, we have this part of the parabola, and then obviously I'm just going to put it in like dashed lines. Hopefully you guys can see this. The dashed lines represent the rest of the parabola just so we can see the symmetry of it, but we're not looking at anything outside of 5. We're only looking to the smaller than 5 and bigger than 0. So we're not looking at anything over here, we're not looking at anything over here. All we're looking at is, for this function, which we know is a parabola, between 0 and 5, find its max value and its min value in that specific domain. Well, we can obviously see that the lowest point is the vertex of the parabola, 3, negative 7. That's why our minimum value is negative 7. Our maximum value, our interval is not even over the vertex. That's why to the right it's not quite as high as it is to the left. This is the max, and in the grand scheme of things we call that a relative max because it's not the highest point on the graph because the graph keeps going up, right? But we could call that the absolute max in this domain or in this interval. And then this point 3, negative 7, that is the absolute minimum of the whole graph, and it's the absolute minimum in this interval. It's both. Okay, so we can kind of use the words relative and absolute a little bit different from time to time when we're talking about a specific interval. Okay, but put simply, all we're looking at today is this. We're looking at a specific interval. We're trying to find if there's any critical numbers in that interval, because the critical numbers would be the points where it stops going up and starts going down, or stops going down and starts going up. And then all we do is we compare the endpoints at that interval and any critical numbers in between them, because the critical numbers would indicate minimums or maximums. Okay, so pretty simple. I'm going to show you one more example of this, and then turn you loose. Okay, so this function is going to be a little bit more complex because you're going to have to do the quotient rule. So it's x over x squared plus 1, but analyze that on the domain 0 to 2, so on the interval from 0 to 2. Okay, so to find our derivative for this one, we have to, like I said, we have to do quotient rule. Quotient rule is the bottom of the fraction, so x squared plus 1 times the derivative of the top, but the derivative of the top is obviously just 1, minus the original top, which is x, times the derivative of the bottom, which is 2x, all over x squared plus 1, the original denominator, squared. And all we're going to do is clean this up as much as possible. When you distribute 1, it obviously stays as 1x squared plus 1. This minus sign goes with 2x squared. So if we think about this, I can clean my derivative up over here. It's 1x squared minus 2x squared. That's negative 1x squared. Bring over the plus 1. And then the denominator is just going to stay x squared plus 1 squared. Okay, so here's our derivative. To find our critical numbers, our critical values for x, we just ask ourselves, and since this is a fraction, we have to figure out when the numerator and the denominator, or what x values will make the numerator and the denominator 0. So if you look at the bottom, it's x squared plus 1 squared. There's no way to make that denominator 0, because no matter what you plug in for x, when you square it, it's either going to be 0 or positive, 0 or a positive number, and then you're going to add 1 to it. So we physically cannot make the denominator be 0. The numerator, it's obviously positive or negative 1. X equals positive or negative 1. Those are our critical numbers, because if you plug in 1 or negative 1 and you square it, that makes it positive 1. But then when you times it by negative 1, you get negative 1. Add 1, you get 0. So for this whole function, the critical numbers are positive or negative 1. However, only one of those is in this interval between 0 and 2. So we don't need to worry about the negative 1. X equals negative 1 and x equals positive 1 are our critical numbers, but we don't need to worry about negative 1. We only need to worry about positive 1. So again, the work today should actually be simpler than some of the stuff we've been doing lately. We take our two endpoints, 0 and 2, and any critical number between them, 1, and we simply plug those back into the original function to see what point is highest and lowest in that interval. So when you plug 0 in, you get 0 over 1, which is obviously 0. When you plug in 1, you get 1 over 2, so 1/2. And then when you plug in 2, you get 2 over 5, 2/5. So 0, 1/2, 2/5. 0 is obvious the lowest number, so we have a min at 0, which is the this point is the minimum. However you really want it, so you could circle both components of that. You could say this point is the minimum, but also its y-coordinate is the lowest point. The highest point, 1/2, is just a little bit above 2/5, so that's our max. We have a max at 1/2. Okay, and again, that's all we're doing on today's assignment. Is we're doing our first derivative test to find any critical numbers, but we're only looking at the critical numbers in that interval. So this interval restriction is what's going to make today probably a lot easier than some of the stuff we've done for the last week. Okay? All right, you guys are doing a great job keeping up on your assignments. Like I said before, I really appreciate that. It makes my life considerably easier when I'm not tracking people down to get their homework from them. So just keep sending me your questions. If they're questions that are pretty isolated, I'll probably just answer them in an email. And if I get a bunch of questions, I'll compile them and shoot you guys out another video going through all those questions tomorrow. Okay? All right, guys, have a great Wednesday. Enjoy April Fool's Day. Talk to you guys later.